Okay, welcome to lesson 6. In lesson 6, we're going to continue with the idea of rotations, but specifically rotations of 180 degrees, which is, as you know, halfway around a circle. And we're going to look at what rotations of 180 degrees do to points on the coordinate plane. And we're also going to learn that when a line is rotated 180 degrees, around a center O, or whatever the center of rotation is, as long as the center of rotation is not on the line, it will produce a parallel line. So we're going to formally prove that and see lots of examples of that. But we're going to start with this example right here, which I'm just going to talk you through. So we learned in lesson 5 that if I have a point, such as P, and I rotate it 180 degrees around a center, that its image lies on the same line as both O and P. So PO and P prime will be collinear when I rotate 180 degrees. So we've seen that. And so if you look at this diagram here, what I have are two intersecting lines, and there's an angle formed by the intersecting lines, 4 angles formed. And you may have learned before that these angles that are opposite one another when two lines intersect are called vertical angles, and their measures are equal. And that is a direct result of rotation. And so what we have here is we have P, O, and Q, which are forming angle M, and Q prime O, P, which are forming angle N. And due to the fact that these are on the same line and these are on the same line, what we have is an angle here that is being rotated 180 degrees. And when I do that, because I know that those points are going to end up on the lines over here, I know because angle measures are preserved in a rotation that this angle must equal that angle. So vertical angles can be proven to be equal in other ways, but rotation is a really quick, slick way of proving it as well. Okay, so that remember that fact that these 3 points, the point, the center of rotation, and the image of the point will be collinear when we're rotating 180 degrees. Only with 180 degrees is that true. Okay, so let's look at the coordinate plane. Okay, and this picture shows what happens when there is a rotation of 100 degrees around center O, the origin, on the coordinate plane. So let's look at what we have. Let's mark our center of rotation is the origin on the coordinate plane. And if we have this point A, we know that point A prime, its image, has got to lie on a line through A and O. So those 3 have to be on the same line. Not only that, they're going to have to be the same distance from the origin, because distance is preserved on a rotation. So when we rotate this, if we look at what are the coordinates of point A, 2, 3, 4, this is the point -4, 0. And the point A prime over here would have to be the same distance, 1, 2, 3, 4. So this would have to be 4 because it's on this same line here. Coordinate, the y coordinate would have to be 0. So the points A prime is, the coordinates of A prime are 4, 0 right there. Now, let's look at point P and P prime. So if I have P here, what I have is kind of an angle there, or a triangle, you could even think of it. The coordinates of P are, the x coordinate is the same as A, so it's -4. The y coordinate is +3, right there. Now, this angle is a right angle. And so when I rotate this 180 degrees, I've got this situation going on. So I know that this distance and this distance have to be equal because the distances are preserved in a rotation of figures like this. Therefore, my point P prime, this distance has to be 3, and the x-coordinate has to be the same as the a-coordinate. So this is going to be 4 and -3. Because I know this distance and this distance have to be the same. Coupled with the fact that this line, these points are going to fall on the same line. So what we've proven here is that if I have a point AB on the coordinate plane, rotation, and I'm going to use some notation here, the rotation around the origin of AB is going to be, let me move it down here, is going to be the point opposite of A, opposite of B. All right, so if we look at our point P up here, A is -4. So the opposite of -4 would be +4. B is +3, and the opposite of +3 is -3. So we're going to use this notation to help us figure out the coordinates of a rotated point. All right, now you're going to complete exercises 1 and 2 on your own, and then come back and we'll do the solution together. So I just want to point out that in exercise 1, it specifies to use your transparency to rotate the plane 180 degrees. And in exercise 2, it says don't use your transparency to figure out what the rotation of a point is. So go ahead and work on those. You're going to use the fact that a point and the center of rotation and the rotated point are all going to lie on the same line. Okay, so pause the video, come back, and we'll solve those together. Okay, so what I want to do to do exercise 1 is I want to start by drawing that line. Drawing that line from the point through the origin and beyond. Okay, like so. So I know that when I rotate this point, the point will end up on that line. So I'm going to rotate just that far. So I'm going to mark, I use my overhead on this one, mark my center of rotation and mark the point to -4. I'm going to rotate 180 degrees until that point matches up to the line. And when I get there, I know I've rotated 180 degrees. So the coordinates of my new point are the coordinates of this point, which would be -2, +4. So I can mark that right here. -2, +4. So my final statement here would be that rotation O of 2, -4 is the point -2, +4. Okay, so in this next exercise, exercise 2, we're given the point again. The center of rotation is the origin. I'm going to still draw my line through the point and the origin and beyond. So I know that the rotation is going to lie on this point. I know that the distance here has to equal the distance to the point. And so it's pretty easy to see that. Also, I know that this distance here between the point and this x-axis line are going to be the same here and here. So it becomes really clear how to find the coordinates of this point just by looking at these distances in this triangle here. So there's a lot you can do. There's a lot of geometry going on here. So I don't want you to just memorize this rule here. I want you to understand why it works. So the rotation around the origin of -3, 5 is equal to 3, -5. Okay, so that's exercise 1 and 2. We made use of what we knew about the point, the center of rotation, and the rotated point being collinear when I rotate 180 degrees. All right, so now I'm going to have you look at exercise 3 and 4. Both of these say use your transparency if needed, and I will probably do that when we do these. Once again, we're going to make use of these facts that we know about rotations, that of 180 degrees, that the points are collinear, and we're going to be this time rotating lines. So I want you to try exercise 3 and exercise 4, and then come back and we'll correct those together. All right, so we're going to look at exercise 3 now, which says to let rotation O be the rotation of 180 degrees around the origin. Okay, we're using this rotation a lot, around the origin, 180 degrees. So line L is the line passing through -6, 6, and parallel to the x-axis. So here's line L, and it's drawn for you bold. So if I want to rotate 180 degrees, basically I could take any point on this line and say I choose this point on the line, draw a line through the origin. From that line, I'm going to find the image of this point, draw a line through the origin right there, draw it lightly. I know that my rotated line has got to go through this point, and in fact these 2 points are going to be the images of one another. But what I can do now is I can take my overhead, mark my center of rotation and my line, and I'll go ahead and mark that point too, and rotate about the origin. 180 degrees is when this point matched up with its the image of that point matched with the original point, and there's my new line. So I can draw it by drawing a line through that point. So this line right here, I'm going to call rotation O of L. All right, and let's look at the next one, exercise 4. This one here tells me the same thing. I've got a line, rotation O is the same rotation. Line L is the line passing through 7, 0. So here's the point 7, 0. And parallel to the y-axis. So I've got this line here now. Now I want to find the rotation of this line. So once again, I'm going to pick a point on the line right here. I'm going to draw a line through the center of rotation, and that will have to be the image of this point. I could pick any point on the line here. And so I know that I've got these triangles here. This point is going to have to end up right over here, an equal distant from the origin. That's my radius of rotation right there for that point. So I could even mark a few other points, but I don't need to because this is going to get me far enough. And I'm going to use my transparency still. rotate around the point, the origin, and here's my line, and that point right there. So let's go counterclockwise this time, since that's what we're supposed to be doing. 180 degrees, keeping the origin together, matching those points up, and you'll see that there's our line of rotation. So it goes through that point and comes down right here. Okay, and we can check our distances. This point, 0, 7, its image should be over here at 0, negative 7, 0. 7, 0, and negative 7, 0. So here is our rotated line. So this is rotation about the origin of line L. Okay, so you are going to use these techniques and work on exercises 5 through 9, and then come back and we'll correct those together. Okay, so in each of these exercises 5 through 9, you should have found that the rotated line, when it's rotated around the origin 180 degrees, the rotated line is parallel to the original line. So let's look at how we can show that. There's different ways. There's not just one right way to do this, but I'm going to pick a point on this line L. It's going through the point 0, 2, but I'm going to pick this point -2, +2, this point here. The image of this point, this is -2, 2. The image of that point is going to be the opposite of both of those. So it's got to be at 2, -2. So I know that my line's going to go through that point. And I could even do that again. I could pick the point 2, 2 here. And the image -2, -2 would have to be on this line. So I can actually just directly draw my line now because I have 2 of the points. So there is the rotated image. And I used what I knew about coordinates of rotated points when they're rotated 180 degrees. So here's my rotation of L, and they are parallel. These 2 points are parallel because the distances to the x-axis are always going to be the same for all of those points. Okay, so they will never intersect in that case. All right, so let's look at this one. This is a vertical line. I can use, let's use a different technique this time. Let's pick a point -4, -2. Draw my line through the origin. To find the image of that point. I can use my transparency to rotate. So there's different methods that you could use to do this, making use of what we know. There's my line, my point of rotation, and I know that this point is going to have to lie on this line somewhere. It has to be collinear. So I'm going to just rotate until that point matches up to the line. I'm getting there. And there it is right there. And then I could draw the line. I could have predicted the coordinates of this point because this point, and it's right here. So there's my point on the line. And I can see from my transparency that this is the line it goes through. So the coordinates of this point were -4, -2. So the reflected or the rotated point would be 4, 2, +4, +2. These two lines are parallel, the rotated line and the original line. Okay, that's 5 and 6. Let's look at exercise 7. Exercise 7 again is, let's see, same rotation, 180 180 degrees around the origin. Let's let line L be a line passing through 0, -1, and parallel to the x-axis. So here's that point, 0, -1. Here's my parallel line. Let's use a couple points here and rotate them. -1, -1 is going to rotate up here to +1, +1. And let's do another one. Let's just pick, we can pick any point we want. Let's pick this point on the line. 3, -1. Its rotation is going to be -3, +1. Right there. So I can draw my line once again. I could have used the transparency to do this. Could have used the fact that a point and its image around a rotation are collinear. So that would have shown me where that point was as well. Okay, but here's my rotation of L. It's right here, and it is parallel to L. So yes, they are parallel once again. Okay, let's look at this one. This one might have caused a little bit more difficulty, but we're going to solve it exactly the same way. So I've got my line L here. Line L is line L parallel to its rotation? Use your transparency if needed. We'll use our transparency on this one, but before we do that, let's find some points here. So here's my center of rotation. Let's look at this point. I'm going to pick some points that lie on grid lines. That point there. Its rotated point, the image is going to have to be on this same line with O. So let's draw that line. Like so. See how I did? I'm a little bit off. You have to be pretty accurate when you draw these lines on the grid. Get my pencil really sharp. Make sure I'm lined up just perfectly. Okay. Might be a little better. All right, so I'm going to use my transparency, and I've drawn a point here. Let's look at this. I have my center of rotation. Don't get confused about which line is which. This is the line we're rotating right here, line L. And here's the point on that line that I know is going to have to be collinear here. It's got to be this same distance from the origin, but somewhere down this line. So as we go, our rotation of 180 degrees, like so, all the way around. I keep going until this point crosses that line. And there's my rotated line. It's going through this point, and it kind of goes here and down. So what do you think? Does it look parallel? And I didn't draw it very straight, but does it look parallel to the original line? And it is parallel. Let's find another point where it crosses a grid line. Let's rotate this point. The coordinates of this point would be 3, -2. So the rotated point would be -3, +2. So let's look at that. -3, +2 would be on the line right there. So that would help me draw it a little bit straighter right here. So there's my line. So this is the rotation, the rotated line, and the original line, and they are indeed parallel. So rotation about the origin of L is parallel to line L. Okay, so exercise 9 has you do the same exercise without grid lines. So, but let's go ahead and use the same method that we've been using. I'm going to pick a point on line L, draw my line through the origin, through the center of rotation, O. And I know that my rotated line, my rotated point here has to be on this line. And it's going to be the same distance. It's going to be over here somewhere. So I'm going to use my transparency to draw this. So here we go. Here's my center of rotation. Here's my point on a line. And I'm going to draw the line. Okay. Now I'm going to rotate around the center of rotation. So I'm going to keep this point anchored and go 180 degrees. And I know I've gone 180 degrees when this point lies on this line somewhere. All right, there I am. So now they match up. So there is my rotated, whoops, there's my rotated point. You know, let me label these. There's P and P prime. So P prime is a point on my line. And now I can just trace my line here. You can see they look parallel, but you know what I'm going to do? I'm going to do this one more time with a different point, and we'll make sure that this is accurate. This is a bit tricky, so if you're a little confused, don't worry. Let's call this point Q. I'm going to draw a line from Q through the origin. Draw it lightly like that. So I know that Q prime is going to have to be on this line, because Q and the origin and Q prime have to line up in a rotation of 180 degrees. So I'm going to rotate one more point here. We're going to do this to find Q prime. All right, and I'm not even going to draw the whole line because I'm just trying to find the rotation of Q. So here we go, 180 degrees, keeping the origin anchored and then matching it up here. And there they cross. So I'm going to mark point Q prime. There's Q prime. So now I know that this line has to go through both of these points because they're both rotated points from that line. So there's my rotation of L. Is right there. So we can see they're it's a little wonky maybe, but we can see that these two lines are parallel by rotating them around the origin. Okay, rotations are require you to do a little thinking here because the points don't end up, it's not like a reflection where they end up just opposite each other. They're going around the circle. So they end up on opposite sides of the circle when we're rotating this 180 degrees. But we've shown that in exercises 5 through 9, that when I rotate a line, I get a line that's parallel to the original line. Okay, we're going to look at the lesson summary, which is on your problem set page, and just go over a couple things here. So what we've seen up to now, both in lesson 5 and 6, is that a rotation of 180 degrees around O, the center of rotation, is a rigid motion, and what happens is that any point P and its rotation are collinear. They lie on the same line. So we saw that happening, that P and its rotation are and the origin are all in the same line. We saw that really in the first example right here, that P, the center of rotation, and P's image lay on the same line. Okay, so we saw that. The other thing we saw was that in the coordinate system, it's really cool because any point AB, when it's rotated 100 degrees around the origin, has coordinates -a, -b when it's rotated. So the rotated point will have these coordinates. So that makes it easy to predict. And we have this theorem too. And let's look at one of our exercises. We did 8. This theorem here in our summary says that if O is a point not lying on a given line, then the 180-degree rotation around O maps L to a line parallel to L. And we saw that again and again. So here's that situation. Here's L. Here's the rotation point, the origin. It's not on L. It maps it to a line over here. Okay. We can formally prove that. And so I'm going to do that now. And you're not going to be held responsible for the proof, but I'd like you just to kind of follow my logic here. So I'm just going to sketch this proof for you. My marker here. So let's prove that theorem. So we've got a line here, call it L, and I've got a point of rotation, O, that's not on the line. Okay, so that's important. Can't be on the line. So if I pick any point, and I call it P, and I rotate it around that image, let's use my ruler here. I'll use a pencil here. So if I rotate P around, then P prime has to be up here somewhere. There's my image of P under this rotation, 180-degree rotation. P prime's going to end up over there. Okay? And so I know that P and O and P have to lay on the same line. And P is a point on L. So the only way for P prime to be on L is if O is also on L, because these have to be in the same line. So the only way for that to happen is for this line to line up exactly with L. But we started by saying that this point is not on line L. So if this point is not on line L, then neither is P prime. So here's a cool thing. This is a proof. And if you followed me so far, do this with me. I could pick any point along L. If I pick another point Q, the same thing is going to be true. Q prime's image is going to lie on the line connecting Q and O, and it's going to be over here somewhere. Okay, Q prime can't be on the line. So what we have is we have all of these points, none of their images under this rotation can be on line L, which is exactly the definition of parallel lines. Parallel lines have no points in common. They never intersect. Okay, so what we've done is we did kind of a nifty little proof here that we showed that any point Q or P or whatever, any point on this line, its image under the translation of O, as long as O is not on the line, is going to give me a point off the line. It can't be on L. So therefore, there's no points in common. Therefore, those two lines can never intersect. So they're parallel. Okay, so there's an actual proof of that theorem for you. You won't be required to recreate that, but I hope you can appreciate just the logic that led to that proof. And so this is just sort of an introductory lesson on proofs again. Okay, so you are ready to do your exit ticket and your problem set.